Hello everybody. We are MD Navid bin Anwar, Muhammad Ali, and James Cease. Today we will be presenting our CSC 579 Overlay and Peer-to-Peer Networking class project on the performance evaluation of the energy consumption in FANET. My name is James, and I will be providing the introduction into our project as a whole. I will also be providing a decent amount of the context as to why the project matters and what other types of projects are related to it. I will then be discussing specifically FANET architecture and some of the general details on how that works. And then I will talk in more detail about applications that FANET is being actively explored as a solution for. Then Ali will discuss some of the challenges associated with the use of FANET in this kind of application. Then he will proceed to talk more about the MAC protocols that we were specifically investigating for the purposes of this project, and will then continue with the routing protocols that we were using in addition to the MAC protocols. After that, Navid will begin with the specific motivations of the testing that we performed for this, and we'll then discuss the simulation setup that we did using NS3. We'll then provide more details on the various configurations that we created in the simulator and the purposes and information that we hope to gain from each setup. He will then talk in more detail about the results that we gained from our simulations and any challenges that we encountered along the way. And Navid will then finish with the conclusion of our work performed on this project. The motivations for our project come primarily from some of the recent areas of growth in the UAV market. For those of you who don't know, UAV refers to Unmanned Aerial Vehicle. These are commonly referred to as drones. Specifically, we were looking at multi-UAV systems. All aircraft, including UAVs, have many different technical requirements that must be met in order to be able to fly and perform their tasks. For our project, we are only looking at a telemetry link. A telemetry link refers to the communication between the UAV and an operator on the ground that communicates the UAV's position, flight parameters, etc. to the operator and allows the operator to change the directions of the UAV in flight. Multi-UAV environments require the ability for multiple telemetry links to connect a group of different UAVs, each to their own operator. They also need to be able to communicate between different aircraft to allow them to share things such as their position with each other. In manned aircraft, there's a system called ADS-B, which is used to broadcast the positions of all aircraft to all other aircraft around them. We decided to specifically evaluate how well a FANET network would work for communicating between the different aircraft and providing their links to their ground stations, specifically emphasizing the power consumption of the system. This is because the less power the radios use, the less power you need to bring on board the aircraft, which will reduce the weight of batteries required, which will in turn allow the aircraft to fly for a longer duration. FANET stands for Flying Ad Hoc Network. An ad hoc network, as many of you already know, is a peer-to-peer network that can be set up using a number of nodes, where each node will forward traffic through itself as required by the other nodes. This can be done fairly simply with devices such as cell phones. It can also be set up in order to be used with moving systems such as cars or other similar two-dimensionally moving vehicles. In that case, it is called a MANET. A FANET adds a bit more complication by moving in 3 dimensions. In the case of the application that we are specifically looking at of UAVs, this means that if one UAV has a link to a ground station, it can share that link with all of the other aircraft in the system. It may not be the fastest link if it has to pass through 6 different nodes to reach the ground station link, but it will still be able to maintain a link. In addition, a MANET or FANET would be able to share information from one node in the system with other nodes within the system. This would allow the aircraft to share information such as their positions with the other aircraft within the system and be able to relay this information to the ground. Groups of UAVs equipped with FANET could have many different applications in many different areas. First, they could be used in disaster relief situations, both to allow multiple UAVs that are performing different uh, tasks to be able to deconflict the airspace so they will be able to move safely around each other. Also, it could be used to provide continuous internet connectivity to the people providing the disaster relief efforts on the ground. Secondly, it could be used in urban air mobility, which is a area that a lot of different companies are actively exploring at this time. It could be used in order to allow large numbers of aircraft that would be operating in a confined urban space to have a lot more information about the other aircraft that are around them to enable aircraft to move through the system much more cleanly and efficiently, while potentially allowing for improved communication between users of the systems with the devices themselves. Also, there are a number of companies that are looking into using UAVs for package delivery. This is being done by DHL and most notably Amazon. This would allow the UAV systems to communicate with each other, with the devices that they are picking up packages from, and potentially with delivery points as well. And lastly, the military slash law enforcement would potentially also be very interested in many different applications that this could have for their specific needs.
Hello everyone, my name is Muhammad Ali and I am presenting to you challenges and UAV routing protocols like AOTV and MAC protocols. With the many applications of UAVs like delivery drone by Amazon, use of UAVs in temporary events like camps coverage and emergency situations such as earthquake or flood, and many civilian and military applications, drones have been used. With all these application advantages, there are disadvantages as well. So first is the optimal deployment. So what is the best way to deploy a UAV so that they provide a maximum service uh, by to perform maximum service or to get the maximum performance out of them, how they should move, the movement of the UAVs are also important. So another challenge is the modeling, channel modeling, air to ground channel modeling, because this affects all the analysis. So it is very important to have a channel modeling for air to ground communications. So the third one is like the performance analysis. So this is related to the hardware design inside. So this is really very low, very low at the hardware level of the UAVs. The third and then comes the energy constraint and the resource management. Both topics has been researched the most, is the drones have the limited energy, so they cannot fly for a long time. So that's one of the drawback compared to the terrestrial network. So while using drones, we have to consider energy constraint as well. MAC protocol. MAC protocol is a set of rules that allow the efficient use of shared mediums such as wireless nodes. In FANET network, multiple nodes want to communicate over multiple hop paths. So this protocol is used to efficiently share the medium for communication among nodes. IEEE 802.11 is used for wireless local area network. It is a set of low-tier terrestrial network technologies for data communication. The WLAN standard operates on the 2.4 gigahertz and 5 gigahertz terrestrial science and medical frequency band. Wireless LAN is used for high-speed data exchange. A typical bandwidth today is 54 megabits per second, and is theoretical possible to up to the 300 megabits per second in case of IEEE 802.11n. So this is just a theoretical concept. So it is IEEE 802.11 has the many versions 802.1a, b, g, and n. So they can be used for the different applications. So on the right side of this is IEEE 802.15.4 is a ZIG B is a low tier ad hoc terrestrial wireless standard, in some ways similar to the Bluetooth. It is a low rate wireless personal area network standard. It is intended to operate unlicensed frequency band. This is a low data rate solution with a multiple year battery life and very low complexity. This standard defines the physical and make clear specifications for sensors and other wireless personal area network. In this slide, we can see the different distinguished features of 802.11 and 802.15.4. So we can see this slide, we can see that 802.11 is better in terms of frequency, data rate, and network coverage range over 802.15.4. However, 802.15.4 has higher energy efficiency than 802.11. And the other thing is 802.11 is a LAN type, whereas 802.15.4 is a PAN type. AODV, Ad hoc On Demand Distance Vector Routing Protocol, is a reactive routing protocol. So in this protocol, routes are created when in demand. AODV discovers a route by broadcasting the request to neighboring node. Like in this picture, S is the source and D is the destination. So S has the it will the route request broadcast a route request towards the destinations using its neighboring node. So S has the destination address, destination sequence, source address, source sequence, and hop count. Whereas the A is the neighboring node that will have the source address, source sequence, destination address, that is the D, and its sequence, and the hop count is increased by the one once it visits it visits from one hop to another hop. It moves from one hop to another hop. The hop count is increased by the one. So A is the two other neighbors like B and C. So B has again the same parameters like the destination address, destination sequence, source address, and source sequence, and we can see that the hop count is increased by the 2. So from C to D, we can see it has reached to the destinations, and the broadcast request from source, it has reached to the destinations now. Once the broadcast request reaches to the destination node D, it will go to the route reply back towards the source, and we can see in the slide every node, every hop is maintaining its the routing table. So we can see here the route will go in the opposite directions. Route reply will go into the opposite directions from D to C, and then from C to A, and then towards the source from where it generated the broadcast request. This slide shows the routing broadcast requests from source to destination, from source A to A, from source S to A, A to C and towards the D. And the routing reply would go from destination D towards C and then A and towards then the source.
Okay, so the motivation of this project in flying ad hoc network or FANET, a small UAV is connected in an ad hoc manner. So these nodes autonomously fly in free space in ad hoc mode to carry out the mission. But the power consumption is one of the major problems that limits the performance. The goal of this project is to demonstrate the impact of MAC protocols on the energy consumption of FANET. So we're going to investigate that how the MAC protocols consume energy and how much it consumes the energy that impact the lifetime of the network or how much the cost effective it is. For the simulation parameters, this is the settings that we have used for our simulation purpose. So the simulator that we have used for this project is called NS2 or Network Simulator 2, and the simulation area was considered in three-dimensional, so like 1000 by 1000 by 100 meters, and the MAC protocols IEEE 2.11, IEEE 2.15.4, or which is known as also the ZigBee, and the channel was wireless channel. For the simulation time, we consider 1/22 or 2 minutes, and the traffic that we have used is called CBR or constant bitrate. The bitrate that we have used is like 2 kbps, and the initial energy of the node we have considered is 100 joule. And for each node, we set the transmission power and the receiving power as 1.65 watt and 1.45 watt respectively, and the payload or the data traffic that we have generated is like 512 bytes per packet. And we also consider the variation of the number of nodes, for example from 20 to 100. It's like 20, 40, 80 and 100. And we consider the node speed is 20 meter per second, so like the every UAV or the devices, for example the drones, are moving with this. In this slide, you can see the simulation is going on using the NS2, and different nodes are transmitting the packets when they have some data to transmit, and other nodes are here and there is deployed and moving freely inside this region. And this model could not, there is some limitation in NS2 simulation visualization because they have only can show the display the two-dimensional, although they are moving in three-dimensional, but this is the limitation of NS2 or in, to show them in. To evaluate the performance, we have considered a number of performance matrices, and one is known as throughput or average throughput that we have considered for the performance analysis. The average throughput is the number of bits arrived per second at the destination node. So this is used to measure of the reliability of the protocol under different conditions. Hence, the average throughput is a network needs to be as higher as possible. That means when the throughput is higher, that means the network perform much better. And there is an equation so that we can calculate the average throughput is NP, which is the number of bits. Then we multiply with the packet size, multiply by 8, divided by the total time for the second. The next performance matrix that we have used is called end-to-end delay. That means it measure in second and calculate all possible delay occurring in the network. When a node sends data or packets, how long it will take to reach to the destination um, is calculated by this end-to-end delay. The average end-to-end delay can be defined as the time calculated for a packet to be transmitted from source to destination across the FANET. And the simple equation that calculating end-to-end delay is defined here. is RS minus TS. RS is the receive time, and TS is the uh, another performance matrix that we have considered here is energy consumption. So the total energy consumption by nodes after completing of the entire routing process of the network. So the total energy needed to transmit or receive a packet can be defined by this equation where E is the total time uh, is equals to TP. The TP means the time needed to transmit or receive a single packet by a node. R is the current and V is the voltage. And when you multiply all together, we could get the total energy consumption into the residual energy is that opposite of the energy consumption. So residual energy means that the energy left after completion of the entire routing process of the network. So for example, at the beginning of the routing, the nodes have the 100% of the energy, and after the simulation, it has remained like 60% of the energy. That means it consumes 40% of energy during the simulation time. So the node has consumed 40%. Or the another word we can say the residual energy is like 60%. For this project purpose, we have shown or analyzes our result in terms of residual. Uh, in this slide, you can see the result analysis. After the simulation, we have collected our data and plotted in different graph to see how the network is performing or how this true MAC protocol is performing. So here you can see in the x-axis we have set the number of nodes like 20, number of nodes 40, then put 80 and 100 that we have previously shown in the simulation parameters part. And on the other hand side, in the y-axis, we have put the throughput in kbps, and this orange line is for MAC protocol 802.11, whereas blue one means 802.15.4. And from the graph, we can see when the number of node was 20, the throughput for 802.15.4 was around 15 kbps. On the other hand side, 802.11 has a higher one, and if we check for the each number of different nodes all the time, we can see the MAC protocol 802.11 has the higher performance compared with the 802.15.4. This graph shows the performance analysis of the number of nodes versus the delay or end-to-end delay. So you can see in the x-axis also the number of nodes, and y-axis is the delay. When the number of nodes is 20, the delay for the both of the MAC protocols is almost same, and very little difference. But when we start to increase the number of nodes, the difference is getting higher and higher. And when the number of nodes reaches to 100, and you can see the difference is really high. For example, for 802.11, the delay is only 5, whereas for the 802.15.4 is gone up to 25 seconds. This slide shows the result analysis of the residual energy and the number of nodes. In the x-axis, we also put the number of nodes, and in y-axis, we are putting the residual energy or the remaining energy of the network. So when the number of node was like 20, there was no difference between, or we can say it's very little difference between these two different MAC protocols. So when we have the 40 number of nodes, the difference between the residual energy starts to increase, and when we reach to the 100, it has the difference is also getting higher. So from these examples of the simulation result, we can see that the performance of 802.11 is a little bit lower compared to the 802.15.4 in terms of energy. So from the result analysis, what we have seen in the previous graph. So now let's talk about those issues, like for the throughput or the on the or the in a different way we can say is network capacity. According to the throughput performance graph, the performance of 802.11 is observed to be consistently better than that of the 802.15.4. And the reason is that the MAC protocol or the MAC layer of 802.11 can quickly and efficiently adapt a higher number of nodes than that of the 802.15.4. That means scalability of the 802.11 has higher performance compared to 802.15. Uh, the the next topic was like end-to-end delay. The end-to-end delay analysis that we have shown from the graph is 802 point perform better than the 802.15.4. That means when a network use 802.11 MAC protocols, the data can be sent faster from source to the destination when compared to the 802.15.4. And regarding the energy efficiency or energy consumption, that we have analyzed using the residual energy, and the result is different from the other two matrices. Uh, it can be observed that the HJ2.15.4 is more energy efficient than the HJ2.11 under saturated traffic condition. That means that when we have the same condition, we put the same condition or the use case for the two different protocols, and we have checked the performance. Although for the throughput and end-to-end delay, 802.11 perform better compared to 802.15.4. However, for the energy efficiency, it lags behind, and 802.15.4 perform well in terms of energy efficiency. So one of the crucial reasons is that 802.11 has contention window that makes it to consume more energy when compared to 802.15.4 technology. In conclusion, for FANET application, according to the performance analysis through simulation, we can see that the IEEE 802.11 perform better in terms of the data rate delay, and no longer it is suitable for example, the longer range, while comparing to 802.15.4, which offers better with a small data size maybe, or in shorter range. So it's a kind of trade-off when the application requires network performance, much not considering the energy efficiency, then 802.11 could be selected. On the other hand side, if the application, for example, the FANET kind of applications, or the IoT type of applications where the energy efficiency is really matters, then 802.15.4 could be the best way, because in those kind of application the number of nodes are really high, so and they are deployed in the short range. So in that case, 802.15.4 will be best options for them. So we can say that if the application requires long range, 802.11 would be good selection. For the shorter range, for example, less than the 37 meter for FANET application, for example. So that is all from our side. Thanks for your attention. And if you have any question, please feel free to ask. Thank you.